20 eV or so. 20 eV is a huge energy spread for hydrogen. It means all the Rydberg states can be excited in inelastic processes. And we had to work very hard to sum all these Rydberg states. We summed up to n equals 9, because once you get above n equals 9, you can use properties of Coulomb functions to simply, it's so close to the threshold to just integrate. And we ignored continuum states because if you ionize the hydrogen, then you could detect that experimentally. So what we had to do is to sum within the bandwidth of our pulse, electron pulse, all Rydberg states here. And this is different from when we did the elastic scattering and Born approximation from the state where we just were scattering from the charge density. So that's the complication when you do the scattering properly. Okay, I'll show you this. And this is the result you get. This is what the electron density is. This is, you've seen this before. So as a function of time delay, you have this breathing mode. The state is expanding. For a coherent state, it's very difficult to define what you mean by elastic scattering. But you could say, let's choose our final state M as 3p, or our final state M as 4p, because we start out with a linear combination of these, and so quasi-elastic scattering would be you end up on either one or the other. And that shows you a diffraction pattern, if you only count these two states, that changes with time in a way that's similar to what the electron density is. If you include all the inelastic processes, you can see some changes. Look, there's more of this color here than here. But you have to be more careful as to how you extract that. Here, this shows you different pulse durations. So most of the, fortunately for electron scattering, most of the inelastic processes happen at small angles. And so if you go to larger theta, and here we have as a function of theta, you can ignore most of the inelastic scattering that happened at very small theta. And you can then integrate for a fixed theta, you can integrate over phi, that's one way of doing it, or for a fixed phi, you can integrate over theta. This shows you the integration over theta. You can see here for different time delays, this is a log scale, so you have differences here between the differential probability. You have a 0 here, which is an image of your target, because this 0 comes from the 0 of the 3p wave function. The 2p wave function in hydrogen has no nodes. The 3p wave function has one node. The 4p wave function has two nodes. And we see in the diffraction pattern zeros due to all three of those nodes of the target wave function. So you're getting some imaging of the target. The higher nodes are at larger angles, theta equal 5, but there are three if one goes, but the cross-section is small. So I just point out this is the node of the 3p. This 0 is due to the node of the 3p, and then you have a reversal of the asymmetry with time. If you go to 500 attoseconds, well, the beat period is 5 femtoseconds, so this is still short enough to resolve that time dependence. You see that here. And my colleague Centurion claims that he will have 100 femtosecond electron pulses this year. So one is getting toward, most people have picosecond pulses, and getting to 100 femtoseconds has been a big experimental advance. If you go to 3 femtoseconds, however, this is the same order of magnitude as the beat period, and so you don't see much difference. There's still a little bit, but you're losing the resolution if you get there. Let's look at this. Robin Santra is interested in diffraction patterns for X-rays. So So he has written several papers recently emphasizing also the importance of treating inelastic processes. In his case, it's Compton scattering processes for X-ray scattering. And
Excuse me,
yes,
to the electron part, I have two technical questions. So those electrons that are not scattered will give you like a Gaussian in the middle of your screen. So wouldn't that wash out the structure that you see?
Yeah, I mean, the interesting stuff happens at a fixed angle theta, and the beam that goes through is within 10 to the minus 4 radians.
So it's very tiny.
Yes.
And the second question is, how many electrons do you have per pulse? So is it like...
A good question. In our calculations, we assume 1 electron per pulse. A problem with electron scattering is that if you have many electrons per pulse, they repel each other, and that broadens your pulse. However, Ahmed Zawiyal has made a big point in his papers that detection techniques are sophisticated enough that even if you only have 1 electron per pulse, you can detect the scattering. You just have to hope that you have high repetition rate to get enough counts. And there are ways to reduce the Coulomb scattering problem. One way to reduce the Coulomb scattering problem, and one that Matthias Fuchs and Martin Centurion at Nebraska are working on, is to make short pulses that have NeV energies, not KeV energies, because when you get to relativistic energies, the repulsion is less important. If the particles are moving very fast, just think about it. If they're spread a little bit, but they're moving 10 times faster, then even though the pulse looks broader, it goes through your target very quickly.
In the MEV case, you destroy the target much more, right?
In elastic scattering, you don't destroy the target. So the primary scattering is elastic, and the energy deposit is relatively little. And it contributes to the inelastic processes, which in electron scattering are confined to small atoms. Okay, so Robin never said how he produced these. You can't use a laser because these have 2 different parities. He just said, you know, let's produce these because you have this left-right asymmetry. And so he was using it for the electron scattering case to show how you can observe this asymmetry. Because these have opposite parities. Whoops. These have opposite parities, and stop it. And so you get a flipping from one axis to another as they meet. They interfere coherently in one side and constructively and destructively. They're interfering, and you get this asymmetry. The question is, when you do electron scattering, can you detect this asymmetry? Well, here is the electron density. It shows this asymmetry for different time delays here. These are the diffraction images. Here's our quasi-elastic results, which show you more clearly what's embedded here amongst all the inelastic processes. But you can see here, this is the diffraction pattern at 0 time delay is symmetric. This is asymmetric. It's asymmetric here at t over 4, whereas this is symmetric. At t over 2, this is symmetric. The electron density is asymmetric. So what's going on? The good news is that you're detecting the asymmetry now. When you treat this as coherent scattering, you can see in the diffraction pattern the asymmetry. That's the good news. Because in the Born approximation calculation, you don't see this asymmetry. You would get the same scattering picture. But the question is, how do we understand this difference at these time delays between the scattering pattern and what's happening with the charge density? Let me show you how you would observe in the full inelastic result. You observe these results. You take an angle theta that's away from most of the inelastic stuff and integrate over phi. That's what this gives you. And you can see here, look, theta equals half a degree. You integrate over phi. And these are 3 different time delays, the curves. This double dotted curve is the highest on the negative z-axis, on the positive z-axis, phi equals 0. And it's the lowest on the negative z-axis, which is phi close to 180 degrees. So the asymmetry is measurable, even including all this inelastic stuff. Now, you may observe that actually what will be done in the experiment is a hybrid electronic motion. Because if you try to populate, as I showed you before, an equal superposition of 3p and 4p, most of your amplitude is still going to remain on the ground state. So we call this a hybrid motion because, here I put the periods. If you look at the beat of the 3p and 4p, you get 6.25 femtoseconds. So that's a relatively slow breathing motion. But the 1s and 3p state and the 1s and 4p state they have opposite parity. So there's a fast wiggling motion with 300 something attosecond beat period. And so one should see both of those in this picture. So in this picture, this is the charge density. And so you can see this slow breathing mode, but very rapid back and forth motion. This slow breathing is going to go away. You see the asymmetry here. Whoops. And so now, if you have a 100 attosecond pulse, you should be able to distinguish both types of motion, both the slow breathing and the asymmetry. So you see here, for an angle of 0.5 degrees, these 3 different time delays, you have asymmetric curves with time delay. If you go to 500 attoseconds, which is longer than this fast wiggling beat period, you lose the asymmetry. These are symmetric curves. And if you look as a function of theta, you see here that as a function of theta, at t equals 1/8, you have, as a function of theta, this oscillatory motion. Whereas here, for 500 attoseconds, you have a flat distribution. This is the difference. This is a measure of the asymmetry, as I'm glad Brett defined this in his lecture. The electrons scattered at 0 degrees minus electrons scattered at 180 degrees over the sum. This is a normalized asymmetry. The slow breathing mode has no asymmetry. It's symmetric. So these cancel and you get 0. And if your pulse is 500 attoseconds, you don't detect this asymmetric fast wiggling. And so the asymmetry is absolutely 0 here, whereas the asymmetry for 100 attosecond pulses is definitely there. Okay, so now I'm going to finish with how one can improve upon ultrafast electron diffraction including inelastic processes by doing some energy resolution of the results. And here, this is our proposed experiment. You have electron pulses, you have a laser that sets up in some target, some coherent state, you set in motion some process. And then after a time delay, you hit it with the electrons, and the scattered electrons are then sent through an energy analyzer, and you distinguish the scattering picture, you distinguish, or you measure the energy of the scattered electrons. Here is a picture of our electron pulse profile for 3 different full-width half maxima of our pulses. So all of these pulses have 10 keV energy. This is a 100 attosecond pulse, 500 attosecond, 3.13 femtosecond pulse. The angular width is 10 to the minus 4 radians. It's the same for all pulses. But the energy bandwidth changes. For 100 attoseconds, the bandwidth is 18.2 eV. So that gives you this spread of energy, so the incident electrons. For 3.65 bandwidth, you have a smaller spread. This is the projection on the lower plane of this. And for 0.5 eV, you have essentially monochromatic pulses. And that's what it looks like. And now this is what you get for the breathing motion of the 3p and 4p states. For 100 attoseconds, you see it looks like there's almost no difference for different time delays, 0t over 4t over 2. For 500 attoseconds, you see 2 peaks here with different time-dependent behaviors. These 2 peaks, it turns out, are inelastic. This peak here is an energy greater than 10 keV, and it's greater than 10 keV by the inelastic process that you de-excite the coherent state, 3p, 4p, to the 1s state. So by de-exciting the energy of the target, the incident electron scatters with higher energy. And so this is above 10 keV. Other inelastic processes involve excitations from 3p to 4p to higher Lindbergh states, and so you lose a certain amount of energy in your pulse, and that's the bulk of this. If you go to 3 femtoseconds, again, there's almost no time change with time. So 500 attoseconds looks like an energy resolution, looks like a good way of detecting the breathing motion of the state. So for a 500 attosecond pulse, if you measure the results of de-exciting the target to the 1s state, you see these diffraction patterns in your scattering plane. Notice that as the time increases, the breathing mode is expanding. And because you scatter most easily from tightly bound states, you get most of the scattering when the target state is the smallest. And as it expands, the de-excitation to 1s decreases, and you get lower scattering. So by measuring the 1s state, you detect the breathing motion, but it's greatest when the target is most compressed. And these are the inelastic processes. You see they're confined close to 0 degrees. This dotted line indicates the most heavy population of inelastic processes. Outside that line, you can see changes slightly. And now, so this is 500 attosecond pulse. This is phi equals 0. That means positive z-axis, 0 time delay. negative z-axis, 180 degrees. This is the de-excitation to the 1s state. This is everything else. And now, as you go to t over 4, 3t over 4, what we did was take our calculated data from the scattering here and subtracted the data you have at 0 to increase the contrast between 0 time delay and the time delay at t over 4. And now you see here clearly, here the majority, the black is more intense here. You have most of the state on the left. Here it's on the right. So your measurement of the 1s inelastic process shows you the asymmetry of the fast this is the wiggling motion of the 3p and 4d states. Sorry, I've changed states here. So this is the wiggling motion of 3d and 4p, which are asymmetric. You get this scattering pattern, you subtract it from the data for t over 4, and you see the asymmetry of this wiggling mode. And this shows you if you integrate over 5 for a fixed theta equals 0.3, 0.5, 1, or 1.5. Let's look at 1.5 degrees here. You can see here the dashed line is the lowest at phi equals 0. It's the highest at 180. So you are able to detect the asymmetric motion of this wiggling mode of 3D, 4D, 4F. Or is it 3P, 4D? I forget. It's 3D, 4F state. And so I want to finish the lecture with pointing out that the momentum perspective is the one to take when you do electron scattering. This is the differential cross-section, as I've explained before. One has to still work out this transition matrix element from each end state of the coherent superposition to some final state of the target. In Born approximation, this transition matrix element looks like this, where B are the Coulomb interaction with the nucleus and with the 2 electrons. This can be worked out analytically for hydrogen. And for hydrogen, if you substitute this result in here, you get this. And so you have a Fourier transform of the coherent superposition state with the inelastic final state of the target. You can do a convolution integral. Sorry, it's not a Fourier, it's a convolution integral of this. You can do this integral, and what you get is the overlap of the momentum state of your coherent superposition with the momentum state of your final measured target. And so it's the momentum state of the coherent wave function that is reflected in the differential probability. Just to give you an example here, you have the incident electron. It exchanges momentum with the target and goes off with Ka momentum. So this is the momentum transfer, and the differential cross-section is proportional to the overlap of 2 momentum wave functions. And this shows you the wave function in momentum space. This is the real part, the imaginary part, because these are complex amplitudes. But if we take the coherent state and square it, you can see that at the time delay, say, of t over 4, this momentum is negative along the z-axis, very small positive component here. So it's asymmetric. And at t over 4, the charge density for the 3D 4F state is neutral, but you can see that this is moving, the amplitude is moving to the left, because at t over 2, this is where it ends up. So your momentum wave function at t over 4 reflects what this state is actually doing in momentum space. It's actually moving that way. And these momentum wave functions are consistent with what you observe in the scatter. Because this shows you here that at t over 4, you have predominantly in the negative z-axis. This is what you observe, and that's what this momentum wave function is marking. And let me finish. So I hope I've shown you that ultrafast electron diffraction depends on the target wave function, not the target charge density. The target charge density can't show you the asymmetries, and the time dependence is not consistent with the observed scattering differential probability. It's the target momentum wave function is what gives you the most insight into what you're observing. And I've shown at the end that energy resolved ultrafast electron diffraction can ameliorate some of the problems with all these inelastic processes that come in and participate when you have a bandwidth of pulse that you have to take into account. And these are references. This is our description of the theory, and this is the description of the energy resolve process. And you should see also this result for time-resolved ultrafast electron E2E momentum spectroscopy. This was pointed out by Lars Madsen to us in 2011, I think, that the E2E process measures the momentum wave function of a target. And sure enough, when we did the calculations, you could understand the scattering phenomena if you do an E2E measurement in terms of the momentum wave function of your target. Or I should say your scattering is proportional to the momentum wave. But in this calculation, we did not take into account inelastic processes. We did hydrogen, which has no inelastic processes if you measure both electron energies. But for a general target, you would have to take into account inelastic processes, and so I didn't present this here. With that, I'll finish.
Thank you. Questions?
So when people make these electron pulses, is
Yes.
there any known method to measure the pulse duration?
Is there any known method to measure the pulse duration? Well, as I said, they have these, they excite from a metal tip electron pulses, and the laser that does it, sapphire laser, you shine it on a metal tip, and you get a burst of electrons every cycle. The electric field points in one direction every cycle, and so that wave packet is 2.7 femtoseconds or so. And then they have this thin lens formula for telling you where you get the minimum wave packet on your target. And, so they have an upper limit on the initial wave packet, and then they can minimize the duration on the target. As long as they're much lower than the beat period or the time period of whatever electronic motion you're trying to measure, then it'll be okay. You don't have to know precisely.
You know, but I mean, so you can know that, okay, this electron pulse is